Bismillahirrahmanirrahim. So our next topic is Coulomb parameters. Coulomb parameters. We will define these parameters in this topic. That what are actual the Coulomb parameters. So first of all, we should have the knowledge about why how momentum loss occurs. Basically, when electrons and neutral atoms collide, let's say this is electron and this is neutral atom, and when they collide, the result is in momentum loss. So hope so this point is clear, that how momentum loss occurs. After that, we will see that on which factors momentum loss depend, and how it can be double. What is the probability of momentum loss? All of these answer you will get in this topic. So let's see the dependence of momentum loss. So it depends on these 3 to 4 things. That number 1, dependence of loss in momentum at angle which it rebounds. So it depends on the angle which it rebounds, mean to say that when something is collide on a particular thing, and when it reflects back, what angle it make with that surface, that's the angle which it rebounds mean. So dependence of loss in momentum and angle which it rebounds, this is the first thing on which momentum loss depend. The second one is head on collision. Head on collision mean to say, if something is colliding with something in a straight line, you may say that. So head on collision, when it is a head on collision, you can say that when electron and atom are in same direction or same straight line, you so same direction, so to say opposite direction. Let's say electron is this word traveling and atom is traveling this word, so their collision is head on collision if there is a straight line in the process of collision, mean to say that it is not deflected by anything, straight collision. So if it the head on collision case, then momentum loss is twice of initial momentum, mean to say that momentum loss would be twice if there is a head on collision. Probability of momentum loss. Probability of momentum loss. What's the probability of momentum loss? So probability is represented by this cross section. Perfect absorbers of momentum. This is nothing but to represent the probability of momentum loss. We will use this symbol to represent our momentum loss. Okay, so now let's have this figure in which you can see electron. This is something some material, and it has area. This is the area, and this is neutral atoms inside it. Everywhere these are neutral atoms, these are the electrons, and it is the thickness of this side. So cross section areas of atoms is equal to sigma. As I already mentioned here, that sigma is cross sectional area. So what we are talking about, probability. So this is the probability that we would represent by sigma. Okay, then electron loses all of its momentum when have collisions with neutral atoms. Electron loses all of its momentum when have collisions with neutral atom. What does it mean? That when these electrons strike with these neutral atoms, then what would happen? Their momentum would be completely converted into the momentum of these now have no momentum, only these have momentum. So their momentum would be shift in these it would have no momentum. Electron would be remain momentumless after collision. Number of atoms in slab is, now why we are defining these terms, that number of atoms is equal to this and fraction of slab, etc. We are about to define a particular term that needs these all of these thing. So first of all, I'm defining the thing that would be the part of that term. So number of atoms in slab is represented by this. So the fraction of slab block by atom is this, and the number of atoms in the slab is this. What is this? This is eta, and representing n in subscript mean that number of atoms, not only one atom, it is number of atoms, so many, they can be so many. So we represent it simple with subscript n, and a is area and dx is thickness as we defined here already. So number of atoms in a slab is equal to this. Fraction of slab block by atom is, when we talk about fraction, that means we have to divide the area by the if we are talking about the atoms, that we are talking about the fraction of slab block by atoms, so we have to divide it by area. So this is what we get, the fraction of slab block by atom. Flux of electrons now is defined by this symbol. You can also define it with f, but here in this book of Francis f.chen, it is represented by this symbol. So this is the flux of electrons. These electrons, when they strike with this, so they have flux this, and when they strike after that, the flux would be this. What is this? This is nothing but fraction of slab block by atom that we already calculated here. So the product of flux of electrons multiply with fraction of slab block by atom, we get the after flux by multiplying these two terms. How can we calculate now total flux? That can be calculated by this, subtracting entering electron flux and subtracting it from after flux of them. So we did it. After that we are just making it to one side. So this is simple mathematics step. This minus this would be this. This is in minus, so we kept this minus in up to the end. Here, when we are differentiating two things, when we are having difference of two things, that can be given by this term. Difference of these two terms is given by this, and this remains the same. Then we divided this term by this term and we get this. Now in plasma physics, we often say that the particular solution of the equation would be this. So we are giving the general thing that this equation would lead to this. f.chen defined the symbol this as reciprocal of wavelength. As you can see here, we have defined this term as a reciprocal of del m, which is nothing but mean free path. So putting this on back equation, we get this, where this is mean free path for collisions. It is a distance at which flux would decreased to 1 by e of its initial value. It is just defined by this in the book, that it would be nothing but 1 by e of its initial value. So we have defined uh, del m as 1 by n. As you can see that we just replace these two. Okay, then if we talk general about, if we know about the equation v is equal to f lambda, it is very famous equation. Actually, we want to calculate what's our end result. So these are the steps that would lead to the end result, that we have v is equal to f lambda, and we know that frequency is inverse of time period, so we change this by this. Now you can define t here, which is the mean time. We can take t here, v here, so get this is the mean time, and taking inverse of it would give us mean frequency. So you can see here I have taken the inverse of it and it become this. After that I'm putting back lambda m, that is this, so put it here. Now if this term go upward, it would multiply by with b, and 1 remains in the denominator. This is the mean frequency that we wanna calculate. In Maxwell distribution, average over particles of all velocity v is called Collier frequency gamma. Gamma is equal to this. Mean to say that we want to calculate the collisional frequency, so that's why we have done all these steps. This is nothing but gamma, the representation of collisional frequency. So hope so you get it. I'll upload the screenshots as well, so that you don't have to worry about the writing. That's it. In this topic we have just see how momentum loss occur, that is by collision. After that we have seen some facts that affects momentum laws. After that we have some representation of symbols that leads us towards the our final equation, that is Collier frequency, which is nothing but the velocity of all the particles when we take the average.